Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. We are in the middle of our discussion of decision models, and I would like now to discuss the solutions of the effective two-dimensional model with you. So we had equations of the type as indicated here, differential equations here for the first population. One of the terms is this transfer function, which we can call big F, or small g for gain function, and a typical shape for this gain function would look like this. Now, let's suppose we have a simple scenario where for a value of 1.0, I would have a readout of 0.9. Or for 0, I would have a value of 0.1. Or for 0.2, I would have a value of 0.2. So I have a simplified curve. And now one of the tricks of the analysis of a two-dimensional system is to identify the points where the derivative is 0. Okay? And now we just plug in one of these points. For example, we plug in the point h1 equal 1.0. That's this point here. We would have a result of 0.9. So if I plug in 1, I have here 0.9. Now I've chosen WEE equal 1.5, alpha equal 1. So this has a value of 0.5. Then I have alpha here equal 1. I plug in h1 equal 1. So this is a 1. I have external input 0.8. So what would be the g of h2 in this case? So the left-hand side is, I look for left-hand side 0. So we have the left-hand side 0. You have minus 1 plus 0.8 makes minus 0.2 plus 0.45 gives a value of 0.25. I read out at 0.25, I have 0.25. Similarly, if I plug in 0.8, I have minus 0.8 minus 0.8. I have 0.5 times 0.8. I would have a result of 0.4, 0.4. And so you continue this way. And then you do the same thing for the other differential equation and fill in that table as well. And this way, you can construct the position of all the points that have ddt h1 equals 0. So this is the axis h1, this is the axis h2, and all the points that have ddt h1 equals 0 lie on this line here. Now all the points that lie on the other function are the points that have ddt h2 equals 0. I have two differential equations, and there are now 3 points where both differential equations are 0, and these are the fixed points of the system. That means there's no change. If the system is here, there's no change. Now suppose we start here. Then there is a change. And I can evaluate the differential equation and I find that the change is symmetric and moving upwards. Now if I'm on one of the curves, for example the curve ddt h1, then there's no change in the h1 direction, which means the arrows are vertically and they are pointing upwards because I have the upward component down here. And they are pointing downward on the other side. And I have horizontal arrows on the blue graph. And now we can follow the dynamics. Suppose we start at a point somewhere here. Well, we are close to this arrow, so we would probably move upwards. And then we cross here vertically, and then we go over here. If I have an initial position here, the dynamics will lead me to a stable state, to the fixed point over here. Now what is this fixed point? It has very low h1, so h1 is smaller than 0, and h2 is big. But the activity of the first group at time t is just a function of h1 of t. So if h1 is 0, then the activity will be very close to 0. If h2 is big, then the activity of this second group will be very high. So this is a point where the activity of the second group is big and the activity of the first group is low. Now, if we follow a point starting here, it would look like this, and we end up at the other point where the activity of the first population is very high. So this is the scenario where I had strong external input to both populations. Now I can keep the strong external input to the first population while reducing the input to the second population. And what happens is that this second curve is now shifted downward. If we now look again at the fixed points, we see that there's only one single fixed point left. Wherever I start, so these are the flow errors, wherever I start, I necessarily end up at this fixed point. So in this case, if you interpret the final state, this here means that the activity of the first population is big, H1 is big, therefore the activity of the first population is also big, while the other population is completely suppressed. So here I had a strong input. H1 is much bigger than H2. H1 was 0.8, H2 was 0.2, the external input. And so only one solution is possible. Now if I also decrease the first input, then I find another fixed point. And this is now a fixed point sitting here. It's again a symmetric fixed point where both populations have very weak activity. So let me summarize. In an experiment, I would start with no input or weak external input. This means small input that's completely symmetric, no bias either one way or other. Then I only have a stable fixed point. Now if I give a strong input to both, it's like having many dots moving to the left and many dots moving to the right. Then two other fixed points emerge, these fixed points here, and these are stable fixed points, and the dynamics will move to one or the other of these fixed points. If only one input is strong, so I have only dots moving to the left, then only one solution is possible, and that's the one corresponding to where the population representing left movement is strongest. So, for biased input, the stable fixed point reflects the input, reflects the bias in the input. If I have strong input that's unbiased, a decision must be taken, and that's represented by the fact that the symmetric solution is unstable, and therefore it's going either to the fixed point on the left or to the fixed point on the right.